All right, I'm going to show you next that you can get this answer without Mathematica. You can get it with your calculator. I mean, of course, you could just add all those up with the calculator, but you could get it in a quick way with your calculator. This is an example of something called a finite geometric series. This sum here. It's a sum of the form some number, I'll call it A, plus A times some other number, which I'll call X. This other number is sometimes called R, and it stands for common ratio, but I want to avoid the letter R, because R stands for interest rate for us. Plus A times X squared, plus A times X cubed, etc. You can either write the last term as A times X to the n minus 1 or A times X to the n. It actually doesn't matter. I think I will write it as A times X to the n minus 1 so that I actually have n terms in my sum. That's the first one. This is the second. This is the third, fourth. This is the nth term. If you call this sum S, there's a nice trick that helps you figure out what it equals without actually adding up all the numbers. A really, really nice trick here. If you multiply both sides by x, this common ratio, by the way, it's called a common ratio because if you take any one of these terms and divide it by the preceding term, as long as it's not the first term, for example, take ax cubed and divide by the preceding term, ax squared, you get x. Ax to the fourth divided by ax cubed would be x as well. That's why it's called the common ratio. Anyway, if you multiply both sides of the equation by x, by the common ratio, something kind of cool happens. You get, first of all, a times x, which I'm going to put here. That thing times x is a times x. This thing times x is ax squared. I'm going to put it right here. This thing times x is ax cubed. I'm going to put it right here, etc. This thing times x is ax to the n, and the previous term times x is ax to the n minus 1. If you now subtract the bottom equation from the top, a bunch of stuff cancels. Do a subtraction. Subtract bottom from top. I'll just write subtract. You might want to write subtract bottom from top. This cancels with this. This cancels with that. This cancels with this, etc. This cancels with this. This cancels with something else there. There's only two things that don't cancel on the right. The a and the minus ax to the n. On the left, I get this minus this, which is the same as s times 1 minus x after I factor the s out. And on the right, I get a minus ax to the n. Now just divide both sides by 1 minus x and you get your answer. I'm also going to factor the a out of the top term. As long as x is not equal to 1 here, because otherwise you're dividing by 0, this is what the sum equals. And if x does equal 1, by the way, that's easy actually. You have a plus a plus a plus a n times. You get n times a for the answer when x equals 1. But if x is not 1, you get this. What does that mean in this situation? What is a and what is x? A is 100,000. X, the common ratio, what I need to multiply each term by to get the next term is 1.08 to the negative 1 power. That's what I need to keep multiplying by to get the next term that I add. So that's x, 1.08 to the negative 1 power. So, let's just do it on Mathematica. You can use that formula with your calculator or Mathematica as another way to get the answer. And with your calculator, it's definitely easier than trying to add up all the numbers, especially if you had like 100 numbers instead of 10. So A is 100,000. X is 1.08 to the negative 1 power. When I raise that to the negative n power on top, n is 10. I have 10 payments. So this is a negative 10 power here. And on the bottom, I have 1 minus 1.08. 1 minus x. This should be the same number. Oh, it's not. It's my problem. I'm not sure what my problem is. Oh, I know what it is. 1.08 to the negative 1 here. My x is not 1.08, it's 1.08 to the negative 1. That. Okay? Formula for a finite geometric sum, we're going to use that a lot in here. We could also find the future value of this annuity. Future value of annuity at time 10 by pushing these amounts forward in time instead of pulling them back in time. By the way, when I say pull back or push forward, it's just a visual. Okay? I'm just imagining doing that in the number line. Take these amounts and push them forward in time to time 10. The first $100,000 has got to go forward in time by 10 years, so it gets multiplied by 1.08 to the 10th power. The next one at time 1 has to go 9 years into the future, so it gets multiplied by 1.08 to the 9th power, etc. The last one only has to go forward in time 1 year. It gets multiplied by 1.08 to the first power. That's also a geometric series, a finite geometric series. I could also use the same formula. The A, if I was thinking left to right, at least would be this thing. And the X would be the same thing as before, 1.08 to the negative 1. You actually can do it the other way around. You can think of this as being the A, and X as being positive, 1.08 to the positive 1, if I go from right to left. You can think of it either way. Kind of cool. What will the answer be? This time the answer will be bigger than a million. These are future values. These are getting multiplied by numbers bigger than 1. So I could do it the way I accidentally did the first one. Like that. The future value is going to be $1.56 million. You could do it that way. You could also use the formula. And let's try it both ways. Let's try it with the A equal to 100,000 times 1.08 to the positive 10, and X being 1.08 to the negative 1. That would be the way to think of it when you're going left to right over there on the board. I'm raising it to the n power, so I need a negative 10 power. I can do it this way. This should be the same answer, and it is. I also, again, over on the board over here, down there, I could also go right to left. And in fact, to keep things a little simpler looking, I could go ahead and multiply 100,000 times 1.08 on the very far right lower corner there as my A, which would be $108,000. Take the X to be 1.08 to the positive 1 power. So when I raise it to the 10th power, I get the positive 10th power. And divide by 1 minus 1.08 to the positive 1 power. This should be the same answer as well. And it is. So you can think of these things in lots of ways. Right? For the rest of class today, about 12 minutes or so, we're going to talk about these income streams or cash flows and their present values and future values. And instead of summations, we'll end up doing integrals. And again, since it is easier to differentiate and integrate, things involving E, we will assume the interest rate is given such that you could think of it as a continuous compounding. Actually, in any given situation, if you allow t to be any kind of number, it can be thought of either as annual compounding or continuous compounding for different r's. It can be thought of either way. But the way the money comes in or goes out is different. It's not discrete payments at certain instants in time. It's continuous payments, continuously at every instant in time. Sometimes called an income stream. I think the book calls it that. Sometimes called a cash flow. The book uses function notation P of t to represent the cash flow. And the units are going to be units of money per unit of time. What is cash flow? It's not money in a river. It's almost money in a river. It's money. Is it money flowing through a window or something through a tube? Okay, it's electronic money flowing through the internet from one account to another. That would be the best way to think of a cash flow. Or maybe lots of accounts into one account. Maybe this cash flow is coming from a bunch of sources. And the simplest case would be to assume it's constant. Let's say it's $100,000 per year. But realize this is happening at a continuous way. So you're not getting $100,000 every second. You're getting $100,000 over the course of 1 year continuously, meaning you're getting not very much money every second. How many seconds are in a year? It's on the order of 32 million. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365.25 days in a year. On average, there's 3.15576 times 10 to the 7th, 31,557,600 seconds per year. So if you're getting $100,000 a year, how much are you getting every second? Well, that many dollars every second. About 0.03 of a dollar every second. So about 1 cent every 3 seconds or so is how we want to imagine getting $100,000 a year continuously. 1 penny about every 3 seconds or so will add up to about $100,000 a year. How much money do you get during a small interval of time? Imagine an interval from 0 to some number, capital M. For us, we're going to take capital M to be 10. So we're going to get this cash flow. It's going to be similar to our lottery example. We're going to get it over 10 years. Consider a small interval of time, delta t. Sorry, it's so loud up there. Time t. I feel like waiting yellow. I won't. At a certain moment in time, you can consider a small time elapsed, delta t, in years. What would that be if it were 1 second? Sorry that I'm making you laugh too much. What would that be in seconds? It would be 1 over that many seconds. Or excuse me, 1 over that many years would be what 1 second is in years. How much money do you get over that small interval of time? Amount dispersed, I'll just say amount, would be approximately the cash flow in dollars per year times delta t in years, when delta t is small. To find the present value of that little tiny amount, pull it back in time, how far? Well, t years. Take that amount, P of t times delta t, pull it back in time, use this formula, because we are going to assume continuous compounding because it'll make our integral easier to do. And this one gives you present values, not future values. The b is represented by this product. You just got to multiply it times e to the negative rt. Times e to the negative rt. That'll be that present value, that small amount. And then add those up to get an approximation for the present value of all the money over the entire time interval. You'll get a summation of things like this, meaning as you let delta t go to 0, you'll get an integral of the product of those two things. Right? Can you imagine in your mind? You add those up to get an approximation to the total present value. Let delta t go to 0. The function is continuous, nice enough. In the limit, you're going to get an integral. The present value of the cash flow overall will be the integral from 0 to m of p of t e to the negative rt dt. And for us, m is 10, and p of t is a constant function, 100,000. R is 0.08. And this is not too hard to do by hand. Zoom in on that if you need to there. You get negative 100,000 over 0.08 e to the negative 0.08 t. Evaluate from 0 to 10. I did this in the last class. It comes out to be negative 1.25 million. And here you get e to the negative 0.8 minus e to the 0, which is 1. And that is the product of two negative numbers. It is, in the end, a positive number. And being a present value, it is smaller than a million in total in this continuous cash flow. You're getting $1 million over 10 years. It's a present value, so it's smaller than a million. What is it? Let's type it in as I wrote it there at the end. Negative 1.25 times 10 to the 6th times e to the negative 0.8 minus 1. Both of those are negative quantities. The product is positive, but less than a million. And also less than the present value for the annuity, where I was getting $100,000 starting right now, and then every year for 10 total payments. It's a smaller present value. And the main reason it's significantly smaller is because with that particular annuity, you were front-loading it. You were getting your first $100,000 right now. Whereas this, your first $100,000 is over an entire year, spread out. So it should make sense because of that, that you get a smaller present value. What about the future value at time 10? It turns out you need to integrate from 0 to 10 your p of t function times not e to the negative rt and not e to the positive rt either. It turns out, you'll see this in the book, you need to integrate e to the positive r times m minus t. You'll see this in the book. Essentially, the reason you need m minus t is because in this picture, at the moment in time t, you've got to push it forward in time by m minus t. You're not pulling it back in time by t, you're pushing it forward in time by m minus t years. And that's why you need the m minus t in there. This ends up being bigger than $1 million. About $1.53 million. Okay, so that's the fundamentals of these present and future values of annuities and also continuous cash flows or income streams. Wednesday and Friday, we're going to combine these ideas, talking with probability, and talk about actuarial applications. And I hope you find it interesting, even if you don't think you're going to be an actuary. Okay, that's it.